Hello students, in today's class we are going to discuss part 2 of module 5 in computer graphics and visualization for 17 series batch. That is curves. Circle of radius r centered at the origin can provide an illustrative example which has constant curvature, which is a measure of how rapidly a curve is bending at a point. The contents goes like this, where we have curved surfaces, quadric surfaces, OpenGL quadric surfaces and cubic surface functions, Bezier spline curves, Bezier surfaces, and some OpenGL functions regarding this. Coming to the curved surfaces, we have the parametric form of a curve which expresses the value of each spatial variable for points in the curve in terms of an independent variable u, such that the parameter u can be defined as x is equal to x of u, y is equal to y of u, and z is equal to z of u. So we can define the other form in the category of non-parametric, where we can define the object descriptions directly in terms of coordinates, that is x, y, and z. If we are using the objects in second degree, such as elliptoids, spheres, torus, paraboids, and hyperboloids, will be having this kind of categorization. A sphere can be a surface with radius r centered on the coordinate origin, which is defined with a set of points satisfying the equation x square plus y square plus z square is equal to r square. So you can see the diagrammatic representation of it along with the equations. Similarly, a torus, which is a donut shaped object which will be having y minus radial raxial of square plus z square is equal to r square. With the pictorial representation you can see. The quadric surface and cubic surface as in wired objects, we can define the OpenGL glut quadric surface functions such as longitudes and latitudes with respect to the functions that are included in OpenGL utility toolkit glut and OpenGL utility, that is GLOW libraries. Similarly, we have OpenGL functions for the objects cone and for the torus. We have already discussed the teapot functions in the teapot program. So you can see wide teapot object and the solid teapot object, how we can define it with respect to GLOW quadratic surface functions. So where we have quadratic object with respect to spheres and new quadratics. Considering the Bezier spline curves, where we consider again the 4 control points P0, P1, P2 and P3. Suppose we still insist on interpolating known values at the endpoints with a cubic polynomial P of u. P0 could be given as P of 0, P3 could be given as P of 1. Bezier proposed that rather than using other two control points for interpolation, we can use them to approximate the tangents. You can see in the equation here, with respect to some Bezier curves, I have defined here a pictorial representations which demonstrate the appearance of Bezier curves. Properties of Bezier curves. The first property defines a very useful property, which is a Bezier curve, is that the curve connects the first and last control points. Property 2 defines another important property where a Bezier curve which lies within the convex hull. Other properties include the basic functions are real, the degrees of the polynomial defining the curve segment is 1 less than the number of defining points, the curve generally follows the shape of the defining polygon, the tangent vectors at the end of the curve have same direction as the first and the last polygon snaps respectively. Coming to the Bezier surfaces, we can generate the Bezier surface patches through the blending functions. If P is a 4x4 array of control points, P is equal to P of ij. Rather than ij, we can use uv also. Then the corresponding Bezier patch could be given with respect to the formula P of uv. Each curve of constant u is plotted by varying v over the interval form 0 to 1. OpenGL includes some of the curve functions with respect to the pictorial representation included in the GLUT library. OpenGL supports Bezier curves and surfaces through mechanisms called evaluators, which can be used to compute values for the Bernstein polynomials of any order. Bezier curves and surfaces to generate other types of polynomial curves and surfaces by generating a new control points. Thus, mechanism is flexible. We can use evaluators to generate 1, 2, and 4-dimensional curves and surfaces. Also, the 3 dimensions. As you can see, we have categorized OpenGL functions, OpenGL spline functions in Bezier spline curve functions, where the type parameter specifies the type of objects which we want to evaluate using the Bezier curves or Bezier polynomials. The control points data are in the array pointed to point array. The value umin and umax specify the range of parameters. For example, in our cube B-spline, we tried 3 points for each curve segments. In the next category, we have glue functions. The glue library uses this mechanism in 4 dimensions to provide NURBS curves. You can see in the OpenGL functions of NURBS. NURB functions can be categorized in 5 important NURB functions such as glue new NURBS renderer, glue NURBS property, glue begin NURBS surface, glue NURBS surface, glue end NURBS surface. The first 2 functions set up a new NURBS object and define how we would like that rendering, and the final 3 used to generate the surface. For NURB curves, the final 3 are replaced by the functions glue begin NURB curve, glue NURB curve, and glue end NURB curve. The glue library provides an additional useful facility called trimming curves. Trimming curves which are closed curves that we can use to render surface from which the areas defined by curves have been removed. The trimming curves are defined after the call to GL NURB surface, and their vertices are specified between calls to GL begin trim and GL end trim, as you can see in the diagram in the OpenGL functions here. That completes your topic of curves with respect to Bezier curves. If you like the video, subscribe it, share it. Thank you.